Welcome to The Explainer. Today, we're demystifying the everyday magic of modern illumination. I mean, if you look around you right now, chances are you're being lit by an LED. They're in our screens, our streetlights, our homes, pretty much everywhere. But how exactly does this tiny piece of solid-state technology actually work? Let's get right into the science behind it.
So think about this for a second. For over a century, humanity basically relied on fire and heat to see in the dark. A traditional incandescent bulb literally burns a metal filament until it gets white hot. But an LED? It's just a tiny, cool piece of plastic and semiconductor material. How does a cooled chip completely replace a burning hot wire?
Okay, let's dive into this massive leap in technology. Traditional incandescent bulbs waste a frankly ridiculous amount of their energy, just generating unwanted heat, which is why they usually burn out after 1,000 hours or so. But an LED, which stands for Light-Emitting Diode, by the way, completely bypasses the heat. It converts electrical energy directly into light. And because it doesn't have some fragile, glowing filament slowly burning out, an LED can last up to a staggering 100,000 hours.
Section 1. Inside the PN junction. The active layer.
To actually see how that direct conversion happens, we gotta zoom way in, down to the microscopic layers hidden inside the chip itself. An LED is built out of semiconductor layers. On one side, you've got the N-type material, which is absolutely packed with extra negatively charged electrons. Then on the other side, you have the P-type material, which is full of these empty spaces we call holes. When we apply a forward bias electrical current, we're basically shoving those electrons and holes toward that boundary in the middle. That boundary is the active layer, or the PN junction.
So here's how this plays out step by step. Electricity enters the diode, forcing the electrons to rush across that junction. When they cross, they literally fall right into those empty spaces, those holes. Now, when an electron drops into a hole, it has to give up a little bit of its energy. And that lost energy? It gets released as a tiny individual packet of light called a photon. Millions of these microscopic events are happening every single second. And boom! The LED glows.
Section 2. The quantum leap. Electron recombination.
Now, to really appreciate what's going on when that electron falls into a hole, we have to talk quantum physics for a second. And this brings us to a really crucial concept: recombination. Honestly, this is the absolute heartbeat of the LED. See, in a semiconductor, electrons naturally want to sit in a lower energy state, which we call the valence band. But when we pump in electricity, we excite them up into a higher energy state, the conduction band. Recombination is just that fundamental quantum event where the electron drops back down from the high band into the low band. That exact microscopic drop translates directly into the light we see.
And it's all backed by this beautiful, simple quantum formula. The energy gap between those two bands strictly dictates the energy of the photon that gets released. The amount of energy the electron loses during its drop exactly equals the energy of the newly born photon, which is determined by Planck's constant multiplied by its frequency. It is just a perfectly balanced quantum transaction.
Section 3. Direct band gap efficiency. Direct versus indirect.
So you might be wondering, if it's all just electrons dropping into holes, why can't we just use any old semiconductor material? Like, why not use cheap silicon? Well, it turns out we have direct and indirect semiconductors. In a direct band gap material, like gallium nitride, electrons jump straight down without needing to change their momentum at all. Instantly, a photon is efficiently born. But indirect materials, like silicon, they require a phonon. That's basically a vibration in the crystal lattice to assist in the process. This extra step adds a ton of complexity and mostly just wastes that beautiful energy as heat. That is exactly why indirect materials are definitely not the go-to for efficient LED design.
It's not exactly a walk in the park even with direct semiconductors, though. Engineers constantly battle two major efficiency challenges. First up is total internal reflection. Because semiconductors have a really high refractive index, a lot of the light acts like it's hitting a mirror from the inside and literally gets trapped inside the chip. Second is efficiency roll-off, also known as droop. When you pump really high currents into the LED, you get a positive feedback loop of Joule heating. That raises the temperature of the chip, which actually reduces the efficiency of the radiative recombination. So it turns out heat is still kind of the enemy, even in LEDs.
Section 4. The physics of color. Band gap and wavelength.
Okay, so we know how the light is made, but how do we manipulate this subatomic drop to actually paint the world in all these vibrant colors?
Remember how we said the drop distance, the band gap energy, determines the photon's energy? Well, the photon's energy strictly determines its wavelength, and our human eyes perceive different wavelengths as different colors. By manufacturing the LED out of very specific materials, we physically change that gap. Indium gallium nitride gives a large drop for high-energy blue light. Gallium phosphide gives a medium drop for green, and aluminum gallium arsenide gives a smaller drop for red. The material dictates the color, period.
Section 5. Creating white light, tricking the human eye.
Red, green, and blue. Great, but what about the regular white lamps in our houses? How do we get that everyday white light? The answer to this is actually so profound that it won the 2014 Nobel Prize in Physics. For decades, scientists could easily make red and green LEDs, but high-efficiency blue LEDs were virtually impossible to pull off. It wasn't until researchers Akasaki, Amano, and Nakamura finally perfected the gallium nitride blue LED that the floodgates opened for a total transformation of lighting technology. Why was blue so important? Because you absolutely need blue light to create white light.
So here's how they use that blue breakthrough to trick our eyes into seeing pure white. There are basically two brilliant methods. The most common one is phosphor conversion. They take that Nobel-winning blue LED and coat it with a yellow YAG phosphor. The blue light excites the phosphor, creating yellow light, and the mix of those blue and yellow wavelengths hits our eyes as a bright, crisp white. The second method is color mixing. That's where separate red, green, and blue LEDs are placed super close together and perfectly balanced to simulate white light.
Let's bring all this highly complex quantum physics, the electrons dropping across band gaps, the direct semiconductors, the phosphor coatings, let's bring it all back down to Earth for a second, to the massive real-world benefit. 100,000. That is the staggering number of hours a well-designed solid-state LED can operate. It's a technology that completely and totally redefines longevity and energy efficiency.
Honestly, I think this quote really hits the nail on the head regarding the monumental shift we've just unpacked. Incandescent light bulbs had lit the 20th century. The 21st century will be lit by LED lamps. We've completely transitioned from relying on primitive burning heat for illumination to literally mastering the quantum behavior of electrons inside microscopic crystals. The craziest part? The science isn't even stopping. We're already seeing the rise of quantum dot LEDs, which use nanocrystals to tune emission colors with pinpoint precision, offering even better color rendering and efficiency. So, I'm going to leave you with this to think about. With materials continually evolving at the subatomic level, how will these new quantum technologies continue to shape and color the future of our illuminated world? Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.